Let's start with this relatively simple question. What is nonlinear optical spectroscopy? So first and foremost, it's basically the only tool which allows you to see molecular action in sort of real time, that is on the relevant time scales. So we are talking about molecular motion. I will use the term dynamics in real time. I mean real time here in quotations because clearly the time scale is such that we can't really see it in real time. But we can slow it down and we can observe it on its own relevant time scales. That is real time and relevant time scales. This means something like tenths of femtoseconds. 10 to the minus 15 seconds is a femtosecond, and we are talking about tenths of femtoseconds. That's the relevant time scale to which this optical technique, this optical spectroscopic technique, allows us to dive. It's an experimental tool. That is important. This is a theoretical lecture about an experimental tool. Experimental tool or set of techniques, set of tools. Which requires a lot of theory. So in order to be understood, deeply understood, we have to get actually around a lot of various theoretical techniques. What is good on this type of spectroscopy is that this experimental tool uses classical light, or let's say quantum light, which has almost classical properties. It is coherent pulsed light. The fact that we are using pulsed light from lasers means that we can time or we can do very good timing on the order of those tenths of femtoseconds, and actually we can do timing which is much better than that. Just the resolution of this experimental tool is on the order of tenths of femtoseconds, because the best pulses that we have would be in this order, let's say sub 10 femtosecond. Now I said that we will be using classical light, but the description that we will have to do for matter, for molecules, molecular vibrations and so on, electronic states of molecules, will definitely be quantum. So this experimental tool requires quantum theory for description of matter. And matter will be molecules, mostly their electronic states, but also molecular vibrations, etc. So another very important point in our considerations will be the fact that we almost never will talk about individual molecules here. The molecules that we study will come in ensembles. They will come in ensembles, which means not individually. In this lecture, we will not get into single molecule spectroscopy and similar things, and also not in gas phase. In most of the cases, the molecules that we talk about will be open quantum systems that are embedded in some environments. So the molecules will be open quantum systems. Okay, that means we will also at some point have to look into the theory of open quantum systems, but we will try to do this as simple as possible. We will basically just get from that theory things that are absolutely necessary. So with this, we can ask ourselves, why nonlinear spectroscopy? So we roughly know what it is or what is it for. We will be observing molecules, atoms with classical light on very short time scales. But the question might be, why non-linear? In fact, we will not be studying at all the non-linearities as a subject. So it's not that we will be studying non-linearities. But rather the task or our goal will be using nonlinearities to study time evolution. Time evolution of, let's say, excited states of molecules, etc. And just because of that, the non-linear spectroscopy in our case is basically a synonym for time-resolved spectroscopy. That's basically our non-linear spectroscopy. There is almost equal in this case. There's one technique that people know best and most, sort of paradigmatic example. Paradigmatic example of a non-linear time-resolved spectroscopic technique, and that is so-called pump probe spectroscopy. Pump probe spectroscopy is the simplest, as we will see, simplest of the techniques, and the one from which we will take inspiration in construction of some more advanced techniques. We will simply see what this pump probe technique will allow us to observe, and we will try to generalize based on the theory. We will try to generalize what else we could do with pulsed lasers in order to investigate dynamics of molecules subject to light. Another quite important information that needs to be, and that's related to our discussion of ensembles, will be the problems that we have with observing microscopic bodies, quantum systems. So we will now have to ask ourselves, how about actually observing quantum systems? So are there any problems that we have to overcome? So let's first think about observing macroscopic objects. So in macroscopic observation, we do not have a problem, or mostly we don't have a problem of timing. We have a single object moving somewhere and we'll try to observe it. When we do it basically passively, we watch, and by watching we do not influence the system. But it's not always as simple as this. You can actually think about the famous bet about whether the horse during gallop, whether it lifts all four hooves above the ground simultaneously. There was a bet in settled finally in 1878 by a man called Edward Muybridge, who used 24 cameras, synchronized cameras, to photograph a moving horse. This guy was a pioneer of ultra-fast photography. He was able to capture the photographs of moving horse and finally prove that it actually does lift all four hooves above the ground simultaneously. So in this case, there was a problem of synchronizing observation with the motion. In a microscopic observation, this becomes an extremely difficult and important thing to do this this type of observation, synchronization. So microscopic observation usually starts with systems that are in sort of equilibrium. So we first have to start the motion. So first we have to start the dynamics. And because this is best done by light, we actually will almost exclusively follow here, or will be interested in photo-induced dynamics. Photo-induced dynamics, to induce the dynamics, that's the task of the pump in a pump probe experiment, and the observation. So we first start and then observe. That's the probe of our pump probe experiment. It's basically almost like the difference between observing a horse and, let's say, a swarm of starlings, because these guys, you will, if they sit somewhere on a tree, you can't see them moving, but you have to start the motion first. With the molecules, there is one additional problem, and that is that when you start the motion, the signal that you obtain from individual molecules interferes and can disappear due to interference. So it is extremely important that you not just start motion somehow, but you start it very well localized in time. And this is the reason for all the non-linearity. So we do the start and observation. So we do start and observation by light. That's photo-induced and then photo-observed, so to say. This is the reason why the response is is non-linear because you have at least two events, two types of responses to different lights that you have to follow. So that's this is actually the reason for non-linearity. And it will be more clear when we start looking at the actual response of the systems from the point of view of quantum theory. Non-linear means that we will be studying a response of molecular systems to higher powers of the electric field of the lasers, for instance. So the way we describe laser light will be by electric field. We will most often think in terms of its polarization and its evolution in time, because we will be looking at one particular molecular or atomic systems. So location of this event will not be that important, and we will be looking at response of molecules to higher orders of fields, so to things like ET square, ET to the third power, etc. And only the theory will actually give us insight into how these orders play out in the spectroscopic signals, for instance, in absorption, in difference in absorption under various situations, etc., etc. Here in nonlinear spectroscopy, we have a very, very tight relation between perturbation theory. This is something extremely important. Tight relation between perturbation theory and the experiments themselves. So perturbation theory is something that will allow us to express the response of molecular systems in terms of the powers of the electric field. But this is not something that we will be using as an approximation. So perturbation theory here will not work in the way that we usually understand it, that is not as approximation to effects, to, let's say, to the observed effects, but the effects themselves, like absorption, like pump probe signal, like some non-linear multidimensional spectra, they themselves are of certain order. So observed effects are of certain order of perturbation in the electric field of the laser. For instance, we can talk about absorption spectrum. Absorption spectrum, if we would conceive it as depending non-linearly on the linearly on the electric field, and this is certainly possible to study absorption of a very strong electric field or a very strong laser, it turns out that in the case of non-linear absorption, we don't have good means to compare results done with different intensities. Different intensities will produce completely different absorptions, and the absorption will depend not only on the studied system, but also on the intensity of light that we sent in. But if we stay in the linear regime, we have a good way how to account for the intensity. We can normalize spectra, for instance, and then compare results done with in different laboratories with slightly different absorptions, because on the amplitude the amplitude of the observed effect does not, or let's say the shape of the effect, shape of the spectrum, does not depend crucially on the intensity of light. It's only linear intensity that we can subtract. So let's have a look at that in a little bit of detail. Now, for now, I really want to emphasize that there is a strict and very intimate relation between perturbation theory and the different experiments. We will want to base all our thinking in future about nonlinear spectroscopy always on the question, what order is the particular experiment in electric field? Very soon we will start looking into the theory of linear absorption. We will try to construct a theory of linear absorption coefficient. But here we'll start with a simple discussion of how this experiment is done and what we can expect, for instance, from its field dependence. So the absorption is usually done so that we have some space in which we put our molecules of interest in some solution, and we send light onto this system, for instance, from here left hand side with certain intensity I0. The light goes through the sample and comes out of the experiment with different intensity. There is a thing that we will actually see justified quite well from the equations, so-called Lambert-Beer law, which says that the intensity of the light diminishes exponentially with the distance. Distance will be the distance traveled through the sample with molecules. So we will have a coordinate system where we have 0 here, and z is the distance. Let's say in our case z will be the width of this cavity or whatever it is with the molecules in question, and the coefficient with which the intensity will decay, this coefficient alpha, will depend on the frequency of light, or let's say the wavelength of light, depending on how you want to think about it. And this quantity alpha is basically the quantity that we plot in that experiment. So here we have omega, here we have absorption. So and absorption spectrum may look for instance like something like this. Some kind of peaks here at different frequencies. The sample absorbs differently. The way that we measure, or what we measure here, is the following. We can have a look at the Lambert-Beer's law and see that I divided by I0, the initial intensity, is this exponential, which already does not depend on the intensity. So if, for instance, the signal would depend non-linearly on the I0, then we would still have some sort of dependence in this equation here. So if we want to be exact, we can, for instance, see that alpha z would be the natural logarithm of I0 divided by I. It's relatively easy to derive here. We can also use a different quantity, which would probably make somewhat more sense, relative absorption. So here we take the difference between the initial and the final intensity. We can divide it by I0, which gives us 1 minus I divided by I0, which basically is 1 minus e to the power of alpha z. And when the absorption is small, we can write it as 1 minus 1 plus alpha z, and then we have alpha z equal to this difference in intensity, relative difference in intensity. So this is it. For instance, this is the way how we strip the information that we are interested in, that is the coefficient alpha, of the dependencies on the exact intensity of light. The second example that we'll do is the pump probe experiment. So in pump probe, we have the same situation when it comes to the studied molecular systems. So we put them into some sort of cavity, and so here are the molecules, and we send first an intense pulse of light, which will start the dynamics, because otherwise the only thing that we could observe with one pulse would be again the same absorption spectrum as before. So this is the so-called pump pulse, which is supposed to induce the dynamics in the system, and we observe with a probe pulse, a second pulse which comes with a delay. If we, for instance, drop these two things on some sort of a time scale, time axis, we would have a delay between the two pulses, which we can call capital T, and this probe pulse will get absorbed. So we will measure absorption coefficient of this absorption coefficient of the matter here, that with, let's say, and without the pump. So we would have with the measurement with pump and measurement without pump. And because we have measured two absorption spectra, we can define something like the difference between two absorptions, which would mean, for instance, something like this, minus a different measurement. So this is with pump, and this is without pump, and this kind of quantity beta, for instance, will be what we are interested in. This, however, because we see that there is no there's this I0 here is always the intensity of the pump of the probe pulse, which acts in a similar way as in the measurement of the absorption. This signal will still depend on the intensity of the pump pulse, and we have to make sure that we know how to get rid of this intensity. Probably we will expect to have some some dependence on the pump intensity, and in order to compare two different measurements, we would like to first get rid of this intensity. And it will be the task of the response theory to tell us what's the dependence of such a measurement on the intensity on the intensity of the field. Hence, the first case in which the non-linearity or the known order of the particular experiment in terms of electric field or intensity of the incoming light comes handy. So we will need crucially this information from the theoretical point of view, but also from the experimental one. If we do not follow, let's say, the order in which, let's say, if we do not perform the experiment with a particular dependence on the electric field, we will not be able to compare two experiments in different laboratories. In the nonlinear regime, this would be extremely important, because there would be extremely difficult, because there would be extremely big changes, or hardly to predict changes of the shape of the spectra, depending on the intensity of the pump pulse. Okay, in order to get rid of such dependencies, we would have to develop a proper perturbation theory of these experiments and properly assign different experiments to different order of dependencies on the laser pulse intensities. The last thing I want to discuss before we start dealing with equations and start to prepare ourselves for the nonlinear response theory is the question of molecules as open quantum systems. So, as I said at the beginning, we will not be studying individual molecules. We will not be studying molecules in gas phase. We will always have quantum systems or molecules as quantum systems embedded in an environment. What does that mean? That means that physically our molecules, or in fact some of their relevant degrees of freedom, so that is the molecule, and to be more precise, its electronic states, will be embedded in an environment of other degrees of freedom, something that is surrounding the molecule and is interacting with it. So this second thing here will be its environment, which might be solvent, or let's say some protein in which that molecule is embedded. That's an important class of environments, but it can also be intramolecular, some other than electronic intramolecular degrees of freedom. So for instance, intramolecular vibrations, in case that we are not actually observing those particular molecular vibrations. So we will have a relatively loose definition on what the system we study is, as long as we are looking at it physically, at some picture of a molecule, etc. But once we start studying with light, we will have to concentrate on electronic states, that is, on those states that interact with optical fields, and all other degrees of freedom of the molecules, including in their intramolecular vibrations, will be put into the environment. That environment often is called bath or thermodynamic bath because it has some definite temperature. And it is in equilibrium. So this whole system, as we have drawn it here, this whole system really as a whole satisfies Schrödinger equation. So the whole system satisfies Schrödinger equation, and namely Schrödinger equation with a Hamiltonian, total Hamiltonian, that consists of Hamiltonian of that environment, of the system itself, and its interaction, and that system as a whole would be described by some state vector psi here and satisfies this equation of motion. The problem is that we are mostly not really interested in the details of the behavior of the surroundings of the solvent, for instance. We want to see what the molecule does under the action of the electric field of the laser and the surrounding solvent, but the state of the solvent is not accessible in this experiment. So we will want to find a quantity, and that's a quantity which is central to the theory of open quantum systems, which describes this system alone. Something that describes the system alone, but is influenced by the interaction, but at the same time is able somehow to abstract away from the Hamiltonian or the exact dynamics of the bath. We know some things about the bath, for instance, that it is initially in the equilibrium or always very close to the equilibrium, and that it has many, almost infinite number of degrees of freedom, but that's all. We don't want to know more. The problem is that we cannot use Schrödinger equation as it stands here for a reduced description, which would go back only to the system S. So we are looking for reduced description, where reduced is really particularly meaning here reduced to the degrees of freedom of the system. There is no Schrödinger equation that would allow or that would be able to describe such an evolution, but we can write down equations of motion for the system alone under the influence of the bath in form of the so-called Liouville von Neumann equation, which we initially write for the so-called statistical operator or the total statistical operator, which is defined as this type of a dyad or projector built out of the state vectors of the system. So this is the quantity which is equivalent to and keeping basically the same information as the state vector psi, but we can derive from it, or by simple action of averaging over the degrees of freedom of the bath, we can define a reduced density matrix rho, which would be a partial trace over all the bath degrees of freedom over this quantity called W, the total density matrix or statistical operator. And we will get in that so-called reduced statistical operator, which carries all the information relevant to our experiment. Basically, when we want to evaluate any expectation value of an operator that depends only on the degrees of freedom of the system we are interested in, that is, for instance, about the electronic states, we can always get this type of information from taking a trace of the product between the reduced density matrix and the quantity we are in, or the operator of the quantity we are interested in. So unless the operator A matters also or involves the degrees of freedom of the bath, unless that is the case, we can always get the expected the expectation values of any operator basically just by taking the reduced statistical operator, or often called reduced density matrix. Our task, of course, will be to figure out what is the, or how the equations of motion for this rho will look like. And an equally important question will be, does spectroscopy or spectroscopic signal depend really only on the rho? I will write it in this sort of simplified way. Does spectroscopy depend only on rho? Would it there not depend on the details of the bath? And the answer is twofold. First, in general, no. There are many things, especially when we have those nonlinear spectroscopic techniques where the state of the bath in between, for instance, the two actions of laser pulses matters. But as a good approximation, often, and that is of course we have to think case to case, yes, we will be able to show basically the whole theory with the assumption that rho alone and some relatively simple equations for rho alone can describe the time evolution or the response of the system. We will build the full theory of every important experiment that we want to look at on that assumption, and only during that theory we'll start to appreciate that there might be situations in which this general no is valid, and we have to go back and have a more detailed look at what is the relation between the state of the bath and the nonlinear spectroscopic techniques. We will be able to show, hopefully in the second half of this series of lectures, that with relatively, in some cases, inexpensive theory, we can take into account the effects of the bath, and that they will be showing, for instance, in the particular line shapes associated with the different spectroscopic techniques. For now, for the next few lectures, we will hope that this provisional yes here will allow us to get to the bottom of, let's say, the basics or the principles of nonlinear spectroscopy, and only once we master those principles, which will give us in some cases, for instance, slightly non-realistic line shapes, we will be always able to step back and adjust the theory, add some details of the theory, which will be able to capture some details of the evolution, of the relevant evolution of the bath. It is well known that optical phenomena can be described with Maxwell equations and basically Maxwell's electromagnetic theory. So let us dive here into Maxwell equations for a start and turn them into a form which will be useful for spectroscopy. So we start with standard Maxwell equations. Let's write them out here just to become a little bit more familiar with the formalism that we'll be using further on. So here we have magnetic and electric fields, mu0 permeability, the current on the right hand side, and we are using for the operation of rotation we are using the nabla symbol. I think this is a well-known way how to write partial differential equations, and we will assume that it is well known to everybody who listens to this video. Check out the internet if that is needed. There should be no big problem to familiarize yourself with this kind of notation. So the second second equation, Maxwell equation, can be written in the same formalism in the following way. Again, we have electric and magnetic fields participating in the equation 2. Then here we have divergence of E equal to the charge density divided by permittivity, and the last equation restricts the magnetic field. So it is well known that with these Maxwell equations we can describe all the electromagnetic phenomena. The electric and magnetic fields are actually real fields related to forces and things like that that we usually use and think about in classical mechanics. But this set of equations can be economically expressed in terms of potentials. So potentials will be, electromagnetic potentials are very useful things in compactifying the equations, the Maxwell equations. For instance, we can satisfy the last of the equations, the equation number 4, by postulating that there is a vector field A whose rotation gives B. So this satisfies equation 4, because divergence of the rotation gives identically 0. It's an identity. So the equation number 4 is then fulfilled, satisfied identically. The similar, I mean, if we replace B with this definition in the equation 2, so equation 2 will give us here the rotation of E plus time derivative of A. We used the definition of B in here. That should be 0, which of course means, again, now we have an equation that can be satisfied by some sort of an identity, because it is true that rotation of a gradient of any scalar function, of course as a function of space, is 0. Then we can say that E plus time derivative of A equals a gradient of some so far unknown function phi, but we can replace this expression by, we can satisfy with any phi. So we already have two equations which we can write it basically here as an equation for E. We can define it with minus here, so that we get minus d divided by dt minus plus gradient of phi. So we have two equations that allow us to identically satisfy. We have this equation here, and we have this equation here, and basically taking any scalar function phi and any vector field A, we can satisfy the equations number 2 and number 4. So we have some more equations, namely the 3 and 1, and those we will use to specify some more precise equations for phi and A. So equation 3 gives us the following. If we use the definitions that we've created so far, we can write then time derivative of the divergence of A minus divergence of the gradient of phi equals rho divided by epsilon 0. That's the equation number 3, now written using phi and a. Here this second term can also be written using Laplace operator, or in another expression it's basically this square of the Nabla operator. We will use this later. So that's equation number 3, and with the equation number 4 we are getting, again, just putting the definitions into the equation. Sorry, this is equation 1. A plus 1 divided by c square, second time derivative of a, plus, and here we will have the part corresponding to the gradient of phi, and that equals minus 1 over epsilon 0 c square j, where we used epsilon 0 mu 0 equals 1 over c square. This is also a well-known formula. All right, so in this equation we can still do some more work, for instance, because there's an identity which allows us to write every double rotation of actually arbitrary field A as gradient of the divergence of A minus here the Laplace on A. This we will put in here. So we have the equations 3 and 4 in a form that they give us coupled equations for A and phi that have to be satisfied in order for the Maxwell equations be satisfied. So we have, with the potentials, we have two definitions of electric and magnetic field in terms of the potentials A and phi, and then we have two equations which tell us which equations have to be satisfied for A and phi themselves. Okay, now there are several ways how one can deal with these equations. They are all based on the observation that if you make a transform of the potential from, let's say, A to A, and adding a vector defined as a gradient of a scalar field. So here we have some arbitrary scalar field, and when we at the same time also change the potential to the potential minus time derivative of this scalar field, that's the same scalar field, we will give this transform will give exactly the same electric and magnetic field. So the same fields. So we have E, which is minus d divided by ta, minus, now if we add the gradient, we will get d divided by dt, gradient of chi. Here we have minus gradient of phi that was present, that's from the definition, and then we add minus the gradient of minus d divided by t chi, and as you can see, these two terms, this one with minus and this one altogether with plus, will cancel each other, and we are getting exactly the same field. For the magnetic field, it's the same situation. We have a rotation of I plus rotation of gradient of chi, which gives the rotation of I So the electric field is unchanged by this transform. So we have a freedom in definition of the potentials A and phi, and that freedom can be fixed in various ways. We fix it by so-called gauge. We will use for our spectroscopy related considerations the so-called Coulomb gauge, which actually consists in requiring that the divergence of A is equal to 0. That can be always done. You can verify that if you would have divergence of A equal to some scalar field, you would always be able to compensate A by adding the transform, the above described transform to it to satisfy the Coulomb gauge condition. So we will assume that this additional condition is satisfied, and going from there we can simplify the equation, Maxwell equation 3 and 1. The equation 3 now would read Laplace phi, that is the nabla square phi, equals to minus rho epsilon 0. This is the so-called Poisson equation, well known from electrostatics. It actually fixes the potential phi by giving the distribution of charge in space. The equation 1, on the other hand, will lead to a wave equation. It's relatively easy to put in all the terms. The term with divergence of A will be 0. That's the only thing that we actually have done here. And then on the right hand side of this wave equation we will have some sort of a source term, which will consist of the current minus a quantity that depends on the time and spatial derivative of the electrostatic potential phi. So this is a wave equation and Poisson equation together. One quite interesting thing here is that in the Coulomb gauge, the electrostatic potential is instantaneous in all space. This sounds very unphysical. There seems to be no retardation. The problem is that the electric field is not defined solely in terms of phi, but also in terms of A, and the combined effect of A and phi together will have all properly physical. So it's well known that Maxwell equations, which we basically satisfied here without any changes, that they correctly take into account retardation and special relativity effects. All right, so now we may discuss a little bit more of useful details, because because this is not what we've done is not yet enough to properly discuss spectroscopy. We also want to separate from each other the part of electric and magnetic fields which pertain to the radiation, and the part of electric and magnetic fields that pertain to let's say electrostatics. This is usually done by considering transverse and longitudinal fields. So if we consider an arbitrary field A, a function in space, we have to use this. There is a Helmholtz, so-called Helmholtz theorem, which states that every such field in space can be written in terms of two fields. One is called longitudinal, the other called transverse, whereas the transverse field satisfies the condition that it has zero divergence. Zero divergence, that is, its divergence in this way equals to 0. The other field, the so-called longitudinal field, has zero rotation. And again, we can write it in terms of an equation. So this is vector product longitudinal field equals to 0. So from this we can see that magnetic field is purely transverse, because it already satisfies the equation that the divergence of B is equal to 0 always. So magnetic field is purely transverse, a purely transverse field. And we also see that the way we defined the vectorial potential, the in Coulomb gauge, we see that it is also transverse. In Coulomb gauge we also have the potential as a purely transverse quantity. Now what about the electric field? What about the electric field? So electric field satisfies the equations 2 and 3. We can split them into the part which has non-zero rotation. That's this, and a part which has a non-zero divergence, which is this one. So these are two equations satisfied by the transverse and longitudinal electric fields. And if we go, so that was equations 2 and 3, and we can, equations 2 and 3, and from the equation 1 we can get this one. We again split. We get, for the transverse part, we get the following equation. Here we have the transverse part of the current. We'll denote this equation by a star because we want to go back to it. And then the same equation for its longitudinal part, we will get the following. We'll get nothing on the left hand side and 1 over c square time derivative of the longitudinal part of the electric field, and here we write 1 over c square epsilon 0. That's basically mu, the longitudinal current, and this we will denote with 2 stars. Now if we apply divergence on the 2 stars, so we'll apply the divergence on the 2 stars equation, what we get is we'll get 1 over epsilon 0 time derivative of rho, That's because of the equation above, plus 1 over epsilon 0 divergence of the longitudinal current. The 1 over c square we have already got rid of, and now we can also get rid of the epsilon 0, and we'll get the continuity equation for the longitudinal current and the charge density. So this is the famous continuity equation, which actually describes the conservation of charge. Okay, now, so that was the second equation, the equation with two stars, which basically describes correctly the electrostatics of the problem. So we have some sort of a longitudinal current associated with the changes of the density of charge. Now we can take time derivative of the equation one star above, and what we get using, actually we can do this using also the equation from above, the relation between the transverse electric field and the time derivative of magnetic field. That's the Maxwell equation 2 in a new form. So we get minus double rotation of the electric field, but this time only the transverse part. On the right hand side, 1 over c square second time derivative of the E transverse plus mu 0 d divided by dt. So the first time derivative of the transverse current. Here we again use the fact that we can write the double rotation as a gradient of the divergence of the electric field minus the Laplace on electric field, because of the fact that we are working here with the transverse field. The first part here is 0, and we get equation, neat wave equation for the transverse electric field, which will have on the right hand side, time derivative of the electric current of the charge current. Okay, all right. Now the only thing that we need to know now is, or we have to figure out, one thing that we don't know about now is what is J transverse. So what's the transverse current? Well, and again here we can quite easily figure out what that is, realizing that E transverse E is actually just the time derivative of A, which is purely transverse, and so on. This works in fact in any gauge, because the divergence of the gradient of phi, which is a scalar function, is equal to 0, and namely always. This is true always. So this works in any gauge. Yeah. So now we can write using the replacing the E with the potential. We can write Laplace dta plus 1 over c square second time derivative, and then again time derivative of A is equal to minus 1 over epsilon 0 c square d dt j transverse, which leads to easily we can get rid of one time derivative on all terms, and we get Laplace on A plus 1 over c square second time derivative of A. So we are heading towards the wave equation in A, and on the right hand side we have 1 over epsilon 0 c square j transverse, and this is actually the equation, the Maxwell equation number 1 that we have already derived, and there we have seen what is on the right hand side exactly at the place where we have the transverse current, and it's the current minus epsilon 0 and gradient of the time derivative of phi. So this is the definition, or this is, yes, basically that's the definition of the transverse current. The longitudinal current we can also determine easily, because it must be, from Helmholtz theorem, J must be J transverse plus J longitudinal, so it cannot be otherwise than that this gradient of the time derivative of phi multiplied by epsilon 0 is the longitudinal current. Okay, and we can also show that the longitudinal electric field, which we don't need for anything, is basically just the electrostatic field. Just to be sure that we written everything that we could, we also write this equation that we are not going to use anywhere later. In principle, we will not use very much of the electrostatics in the rest of the lecture, but it is important to realize where our starting equations come from. On one hand, we are related, or the theory will be based and related to Maxwell equations, that is the classical electrodynamics, because the field is classical, and the sample of molecules behaves in general as a classical medium, but the state of that medium or response of that medium is influenced by the details of the quantum dynamics of the entities that compose the matter. And that is the next step we will do. We'll try to relate the microscopic theory or some microscopic model of the molecular systems with some quantities that we already have in our equations. In particular, in the equation that is here now in the center, the equation for the electric field, because by this electric field we will be describing the action of the laser field on the molecules, or laser light on the molecules. So the most important result of our discussion of Maxwell equations is this wave equation for the transverse electric field, which has the right hand side with the transverse current, and we will use this equation to connect the microscopic theory of the samples, or of the ensemble of molecules, with this macroscopic Maxwell equations. So here at this very place we will not do anything big. We will just say that we will relate this current, the transverse current, to some oscillatory motion of charges in the molecules. So we will have charge q and the vector of velocity of that charge as basically that will be the definition of J. This quantity will in fact be some average over space. It will be a quantity always defined with some coarse graining, some small volume in which we can define one value for the polarization of the sample, let's say the motion of the dipoles, or let's say of the charges inside that small volume, the charges representing the molecules. And we will connect this to time derivative of the expectation value of some quantum mechanical operator R. So this is the position operator of the of electrons, for instance, electron charge, etc., all averaged quantum mechanically and averaged over space. And this is, if you look at Q by R is a polarization. That's basically the definition of polarization. The same way that this is a current, so time dependent, the time derivative of the polarization is the current, and we can write it, because this is again some sort of averaged quantity, we can write it as a time derivative. I will write this type of time derivative of the polarization vector, the macroscopic polarization vector. This is how the microscopic theory that we not do at the moment, but we just show how it can be done, or how polarization as a macroscopic quantity is related to something quantum. We show how this is done, and we will now use it in the Maxwell equation. So assuming that J transverse can be written as a time derivative of polarization, we rewrite our Maxwell equation or our wave equation in the following way. With the right hand side, which contains 1 over c square, and here we have the time derivative and 1 over epsilon 0 multiplied by the polarization. This is a function, this is a field, basically, exactly right like the other quantities here. E depends, and the polarization also depends on time, but I don't write it explicitly. So now if we try to do Fourier transform of this equation, Fourier transform in time, so from time we go to frequencies and space, so from R we go to wave vector. Actually, the wave vector transform is not as important here at the moment, but if we do this type of Fourier transform, we can write for the P of omega, the Fourier transform of the time dependent field of polarization, we can write the following linear dependence on the electric field. This is a well-known response theory, linear response theory. This is called susceptibility. And in principle, there can be any power of E here and susceptibilities of higher order, but this is a linear, that is the first order susceptibility. Epsilon 0 is defined here just to compensate for this epsilon 0. We also have to take into account a couple of other facts. So the Fourier transform of a spatial second derivative of E will give us minus k square. That's the length of the wave vector. And here we will have E transverse omega minus, now we will have plus omega square divided by c square. The omega square comes from the Fourier transform of the second time derivative. And here we have again omega equals, and here we have again omega square divided by c square, and the Fourier transform of epsilon 0 p will be chi omega E transverse omega. So we have an equation in which we can put everything to the left hand side. We can write minus k square plus omega square divided by c square. Here we will have, actually on the right hand side, we will also have to write minus. So here we will have 1 plus chi omega, and all this is multiplied only by the e omega and equals to 0. This means in order for this to be satisfied, that this has to be equal to 0, and we have a condition that k square has to be equal omega square divided by c square multiplied by the 1 plus chi omega. So this 1 plus chi omega is a quantity, or we usually call this quantity relative permittivity, epsilon r, and as we can see, it depends on omega, and it is related to the linear response of this type of linear dependence of the polarization on the electric field. It's an induced polarization to the first order. Now this k here enters the equations of motion, or let's say the solution, spatial solution of the Maxwell wave equations, as e to the power of I k z. So this is the dependence of an electric field which goes in one direction, defined by this let's say coordinate z of the coordinate system, and the vector k is then defined as having the x and y coordinate 0, and here we have the whole length of the vector in the z. So this is the field going in one direction, and it evolves in space according to this equation. We can draw simply, let's say, the real part of the e to the power of ikz. The real part is a cosine, so it will look like this, for instance, within a constant amplitude. Constant amplitude if this k is real. However, now we can write here that k is equal omega divided by c and square root of epsilon r, and epsilon r in fact does not have to be real. So we will define the real and imaginary part of the square root as n plus I kappa. So this is the real part, and this is the imaginary part of square root of epsilon r. And then we will get something else if the imaginary part is not 0. We can actually get a decaying amplitude of the field, which is precisely what we would expect in terms in case of absorption. So e to the power of I k z will now be e to the power of I omega divided by c n. That's the refraction index actually, and a second term which will look like minus omega divided by c kappa z. And from what we have already said about the absorption coefficient, where we expect absorption coefficient, we know that the amplitude of the, or let's say the intensity of electric field of light, or of intensity of light, will depend like this on the coefficient and on absorption coefficient and z. And we can see that because this is what we have here is proportional to the electric field, or that's the electric field, and intensity of light is proportional to the electric field squared. We will have here I0 e to the power of minus 2 omega kappa divided by C Z, which means that the absorption coefficient alpha is equal to 2 omega divided by C kappa. And now we just have to figure out what is kappa, because kappa is not simply an imaginary part of the 1 plus chi, that's the quantity that we have defined, but it's a imaginary part of its square root. So we have to, before we actually finish this, we have to go into some more detail. So we have epsilon r is 1 plus chi omega, which can be written as 1 plus chi dash omega, which is the real part, and here imaginary part of the susceptibility. It's the imaginary part, and square root of epsilon r is then equal to square root of 1 plus chi plus I chi. Well, the real and imaginary part, and that is n plus I kappa. And we want to know what is n and what is kappa. This we can achieve by first taking a square of this equation. So 1 plus chi dash plus I chi 2 dashes is equal to n plus I kappa, n plus I kappa here, which is n square minus kappa square plus 2in kappa. We can take the real and imaginary part of these equations. So first we get, from the real, we get 1 plus chi dash equals n square minus kappa square, and I chi 2 dashes is equal to 2in kappa. That's the imaginary part. So from the imaginary part we can write an important result, that the kappa that we are interested in is chi with 2 dashes divided by 2 times the refraction index. And from the other equation, there we can see that kappa square is this absorption coefficient square, so probably something relatively small. So we can say that 1 plus chi dash equals n square plus chi square divided by 2n square, which we assume is something very small. And from this we can get that n is equal square root 1 plus chi dash. That's the real part of the susceptibility. So these are very important results, and we can all together sum up an equation for the absorption coefficient, which depends on frequency and looks like omega divided by n c chi 2 dashes. That is the absorption coefficient, so is proportional up to some little frequency dependent factor to the imaginary part of the susceptibility, of the linear susceptibility. And for the rest of this lecture series we will actually look with the most, or we will have a detailed look at how susceptibilities of higher order, and in fact we will be looking at them in time domain, so the so-called response function of higher order look like, because just as the linear response is driven by the susceptibility of the first order, higher orders actually drive the higher order non-linear experiments, in which we will finally be able to also find time resolution for the processes that occur in molecular systems.